Hi, welcome to this video on electrochemical aptamer-based biosensors or sensors, EABs. So in this, I will discuss EAB, how to kind of, in very broad terms, how to identify the aptamer, and in very broad terms, how to maybe get a signal out of an electrochemical aptamer-based sensor, an EAB. Just to sort of say that we have SELEX, this systematic evolution of ligands by exponential enrichment, which is really a kind of sequence of start off with I'll describe it. Start off with a library of potential aptamers. These can be sort of single strand RNA or DNA. You may have a target that you're interested in, and at which point then you will take this kind of random pool of potential bindings and add the molecule or the analyte of interest, and there'll be a binding event, and then you're going to have to purify that. Now, I've been keeping this very generic, but we call this kind of partitioning. So you start off with a library, you get a binding between one of the members of the library, and then you have to kind of essentially separate out what bound and what didn't bind, at which point now you can amplify. If it's a DNA based binding probe, then we can do PCR, polymerase chain reaction, and if it's an RNA, we can do RT-PCR, reverse transcriptase PCR, polymerase chain reaction. So we amplify the binding, those that look like they're binding, and then we can essentially iterate around this cycle several times, because there may be several members of the library that actually bound, and you'll essentially amplify them all, and you'll go through this sequence several times, because it will help you sort of single out the best binding motif for that particular analyte. So that really is SELEX. Now, SELEX is really good when you're just really trying to optimize for binding in the homogeneous phase. So I think I'll describe it here, in fact. So we have kind of a potential binding agent, and we have the target itself, and SELEX is really good at sort of optimizing on that particular binding event. It also has other secondary things that it's optimizing on, for example, the ability to amplify the capture probe here. If it's very good at being amplified, then it will also kind of come through the SELEX process quite well as well. But when we're talking about electrochemical aptamer-based sensors, EABs, in reality, these are not homogeneous phase binding. It's actually heterogeneous phase binding, and that's because we're actually going to immobilize the aptamer on the surface, and then probably the analyte will then sort of bind to that surface and cause either just binding or binding plus a conformational change. The problem with SELEX is that when it's, let's say, optimizing, it's only optimizing on binding, and it doesn't feel any kind of, it doesn't know anything about your later application where you're going to actually try and tether this to a surface. So there's no indication of how well this aptamer is going to behave when it's actually on a surface. There's a specific environment, probably being on the surface. You could have a slightly different pH. There's certainly be something called a double layer, for example. So there's no, as I say, any kind of account of that in the SELEX process. It's also probably worth saying that for an electrochemical assay to work, the electrode has to have a certain sort of distance from the molecule that's providing electrons, the reporting molecule. And that's typically less than 4 nanometers. So we could call that the Debye length. So we like things that are fairly near the surface. So the SELEX process doesn't know about the surface, and therefore it's not optimizing for the surface, and therefore it's certainly not optimizing for giving you a binding event that's somewhere near the surface or causes a change somewhere near the surface. And SELEX process is not thinking about an electrochemical signal. So for example, if we want to put methylene blue as a tag on there, the SELEX process is not really thinking about whether that binding will cause the conformational change, and you'll get a signal due to the switching of methylene blue from one conformation to another conformation on your aptamer. So I think I say it here that SELEX is primarily optimizing for high affinity binding in the solution phase. And so as powerful as it is, it's not necessarily designed to give you the best aptamer for electrochemical biosensing. what we are sort of advocating is really kind of, taking a literature search at this. I mean, the one thing about electrochemical assay development, especially EABs, electrochemical aptamer-based biosensors or sensors, there's loads and loads of literature out there. So, do a literature search, then maybe do an in-silico triaging, because when I say in-silico triaging, it's basically trying to model to see whether that has kind of flexibility in it. So if it has flexibility in it, an aptamer that is upon binding, if it does a conformational change, that could be useful for electrochemical signals. Check whether you can actually add something like a methylene blue label. You sometimes need spacers. So when I say spacers, you want the aptamer somewhat, it has to bind to the surface probably through a thiol bond. That's a sort of self-assembled monolayer. And you probably need a certain number of spacers between the thiol, or between the surface of the gold, for example, and the main aptamer site. These additional features to the aptamer could disrupt the folding. You also want to kind of check, the one thing about aptamers, antibodies kind of have their structures kind of fixed by the amount of, let's say, binding within the molecule. So an antibody, I think, has quite a good conservation of its structure. Well, an aptamer actually has a sort of structure that's pretty dependent upon the solution that you're in. The pH, the salt concentrations, the salts that are there. So in reality, if you were doing SELEX, and SELEX wasn't reflective of the actual assay conditions, so for example, if your assay was going to take place in interstitial fluid, that might be different from the buffer conditions that SELEX was done in. So it's probably worth doing a literature search around biosensors for detection in ISF, interstitial fluid, if that's what you're interested in. It's very important to avoid, to do some in-silico modeling to avoid unnecessary secondary structures. An obvious secondary structure would be you have an aptamer that has some sort of repeat units in it. And that could encourage aptamers to actually bind to aptamers. So rather than having a surface of aptamers all pointing upwards ready to bind, you've actually got some aptamers that have hybridized. So in fact, they effectively bound with themselves, and that will weaken any signals that you would otherwise expect. And also you've got to think about the fact that this thing is going to bind. So we have to think about the bound and unbound conformations, and whether on binding it does cause a useful conformational change. The thing about electrochemical EABs, electrochemical aptamer-based biosensors, is that we can have lots of ways of actually picking up a signal. We can have a sort of tertiary assay where we have aptamers sort of coming up from the surface. I show them here in kind of this red rectangle. They bind to the target, so there's a target, so that's great. And then actually we can have a reporting and in that particular conformation, there is essentially no signal. But then if we have a reporting, let's say aptamer, that's also binding to the target, it's kind of like a classic sandwich ELISA assay. But here it can bring a reporting molecule in. Now, the one thing I should say about this is it's that reporting molecule, for example, could be methylene blue. When I say reporting molecule, I'm thinking about that yellow circle there. It has to be within about less than 4 nanometers of the surface for us really to pick it up. Otherwise, it is screened by something that's called the Debye screening, or otherwise the Debye length. But those are assays that one can develop. Now, a sort of simpler assay could be that, in fact, you've just got binding. So effectively, you've had a SELEX assay, which has only really been optimized for binding. Fortunately for you, the aptamer does actually bind to the gold surface, which is great. So the target kind of comes in. It's binding then to the aptamer, which is bound to the gold surface, for example. And then, and I say the gold surface, I should point out that Zimmer and Peacock has gold screen printed electrodes, which I will link to underneath this video, and which will be useful for this kind of work. So we've got, for example, here a reporting molecule that wants to get to the surface. So in the absence of binding, the surface is quite open and we get a strong signal, and then upon binding, in fact, the signal decreases. So that's in that particular case, I could call that a blocking assay. Though sometimes binding can end up promoting the electrochemical reporting molecule to actually get to the surface. Don't always expect a negative, let's say, a decrease in the signal necessarily. Another assay that's applicable to EABs is actually intercalation. So you have an aptamer, it binds to let's say a molecular signal that you may have got from a bacteria or a virus, for example, and then you can detect it. You can detect that hybridization between the capture probe and the target by intercalation with something like methylene blue or Moldala blue, something that will intercalate into the grooves of the now hybridized molecule. I suppose that works best with probably DNA. And then you get a potentially positive signal upon the binding of that intercalating molecule. So I bring that up because SELEX is great for optimizing on binding, but then I'm kind of saying, well, SELEX has a problem, which is it's really just it's just optimizing for binding. But of course, with EABs, you actually have to think about the tethering to the surface, and then how are we going to get a signal out of that. I think one of the most classic ones when it comes to EABs, and it's quite elegant, are these kind of hairpin configurations where you'll have an aptamer with something like a methylene blue on it, and you'll get a strong signal, and then the idea is that upon binding, it causes a conformational change and the signal will decrease accordingly. So in summary, SELEX is great, but it's really optimizing on homogeneous phase binding. In reality, electrochemistry EABs are actually heterogeneous binding, but actually you can both do a literature search and then in silico triaging or modeling to make sure that actually you can get a signal out of this. If you do have any questions about EABs, I will link to the ZP gold screen electrodes as well. Then essentially don't hesitate to reach out to us. Okay, thanks very much.